Rant 185, and I am back inside. I'm recording this right after 184, but they won't be released at the same time. Okay, so this is the misunderstood Penokean orogeny. I did this. It's actually in one of the publications of the Institute. It's available on Amazon. And this is how I do these. If I publish it in a month and then a year, and then I'll do like 1A. If there's a B after it, that means it's a second edition, C's a third, etc., etc. And this will be the January 13th, 2023 update, because I'm not getting it done before then. This is by no means complete, but I just want to show you some stuff in here. All right, we're going to go through that. Here's the abstract, basically telling you about the Penokean orogeny. I'm not going to read this. You can read it for yourself if you want. This is the introduction. Like I said, this is still work in progress. A lot of it still needs a lot of editing. This is basically the location map of, wait, what is that? Yeah, basically we're going to focus around here. This area is where we're going to focus on. I actually did pull some more samples from over here. Some samples you saw in the shedder from over there. So I got to update this map too. I haven't done that yet. This is the traditional concept of the Penokean orogeny. Now I'm just going to show you this here real quick. This is Sim and Schultz 1993 map. Bailey and a bunch of others back in 1966 did more detailed maps than this, but this is a good compilation. As you can see, the general area of this map is, come on you, I'm trying not to have dead air here, and a lot of units, is this area. There's Lake Michigan, Lake Superior. It's in this pink area. So it's a pretty good sized area, but it's not really detailed because this is a smaller scale map because it shows a larger area, so it details less. But this is what I want you to get out of it. This area here, these greens and these pinks, this is the Pembine-Wausau terrain. This terrain was accreted to the Superior Craton circa 1.85 billion years ago. It's a little wider time frame than that, but here's the problem. This fault right here, the Niagara Fault Zone, you see it listed here as a fault zone. This has been traditionally modeled as a continental suture. Now let's go back to here. What that means is the Pembine-Wausau terrain, this is the traditional model, came from somewhere. No one addresses its origin. It just came from somewhere and accreted to the Superior Craton. See, this is modern north. Oh yeah, and just so you know, north on this map is to the top, okay? So this would be the Niagara Fault Zone, the suture, and then the Marshfield terrain came later. The Marshfield, we'll talk about that briefly. So this would create a continental suture sandwich, or such as the Niagara Fault Zone, in principle, if this model was correct. However, the Niagara Fault Zone has never been found, and a continental suture like this would leave a huge scar. We would see some surface expression of this, and the more investigating I do, the more I come to the conclusion it just didn't happen. So originally last year, I thought maybe Z's model was correct, that maybe the Pembine-Wausau and the Marshfield terrain were in situ, and that a subducting plate did a little rollback, and we had some volcanism associated with that, creating this. Now, I knew at the time there were problems with this model, and I even said in here that it needed hashing out. But no, it's not. We've pulled zircons from the Pembine since then, and more detailed the Marshfield terrain. That is Archean. It does have an Archean core, and it was accreted after the Pembine-Wausau, so it's a continental fragment. And based on the geochemistry that Malone and others did, it probably split from the Wyoming craton or terrain, which is a talk for another time. But the Pembine-Wausau shows no evidence of a deep-seated Archean base. Now, so what I did here, you see this approximate line of cross-section here? The green's the Pembine-Wausau terrain. This is a Wolf River event. That thing's a whole other thing. The bluish-gray here is a mid-continent rift. You can just read it over here. Oh, I cut that off. That's supposed to be Superior Craton, which is this brown area here. And this is the Marshfield, and this is something we're not even going to address. It came later. And some of you have seen this. I did this in a video before. This is my working hypothesis now. So here's your A to A prime. So this way is northeast. So A to A prime, and that holds for all of these. Basically, what my hypothesis is now is that we did have subduction initiated here, because we do know this would be the Orogeny, and we do know those are passive margin sediments. So we had a successful rift that became a passive margin, and according to the Wilson cycles, that passive margin would eventually close, that ocean basin would close. And that's what happened, but how did it happen? So I have it going as the plates, went down and started subducting under the Superior Craton. This is your Nipissing intrusions. They're related to that, I think, but they're also related to something else. What is it? Ngava, I believe. Dike swarm is what they're related to geochemically. But they are a little more distinct. Sorry, I got some sinus problems going. Oh, and I also got my flu and latest COVID shot. So, yeah, I'm doing real good here. And these are millions of years ago. MA, that's what it means, million mega annum. And this is what I think happened. I think that we had a hotspot type scenario. As this began to dive, we got a little bit of plate rollback. That caused extension here, giving us the beginning of what would become the Pembine Wasa. So as green as your ocean crust. And you start getting magma up here. And as this rose, this rollback continued, and we got a little bit of extension here. Now, this space here, 200-300 kilometers we're talking here. So this thing didn't form too far off. And Iceland isn't too far away from Greenland right now either. It's a little further than that, but it's a kind of hot spot scenario. It was probably shallow initiated instead of deep-seated hot spot. And this thing continued to develop. You get lava flows, the yellow are sediments, and the green was just to differentiate the Pembine Wasa as magma cooled and started to, rip up the ocean crust. Eventually, subduction here stopped, and you kept getting mantle. And these are the felsic plutons, the pink. So everything stopped for a while until you started getting subduction here. And this subduction initiated subduction here. I know this sounds overly complex, but their field evidence shows that because we have no phyllite here. This really light blue-green. So it had to get accreted somehow. So there is justification for this. And in Minnesota, there is evidence of a south-dipping ocean crust in the seismology that it might still be there. So we got this double subduction just building this Pembine Wasa terrain up even more. And here comes the marsh field after being separated from the Wyoming Craton and plows into this whole thing, shuts this whole thing off. And 1450 million years ago is just about the time of the Wolf River event, which is a talk for another time. So that's the model. Now I want to show you guys this real quick. Sorry, this is going to be a little longer GeoRant. Apologize. But this is good because I had to print it on 8.5 by 11, so I had to divide it up. But this here is a lot better. You see this is me trying to correlate. This hasn't changed much. What has changed is some minor interpretations. Now you go back to here, and you see this brown here. This brown is basically Michigami Formation, which is interpreted to be mostly clastic sediments, slates is what it's become. Some places metamorphosed to schist facies. Down here, all of a sudden, to keep this fault here, this is all quinnesec, which is lava. But we have lava in this. Like, this is the Badwater greenstone. And here we have sediments in here. Like, I've taken you guys to, and I did a video about Pierce Gorge, which that stuff has traditionally been interpreted to be lava, but it's clearly sedimentary. It has freaking clasts in it of sturgeon quartzite, and it shows no baking or anything, so it's obviously sediment. I got a picture of it right here. Here it is, right here. Pierce Gorge. That's sturgeon quartzite. So this isn't igneous. There's no baking. There's no anything. This is sediment. This is gray wacky. What the traditionally called the gray wacky. And so it seems that what's a lot of the stuff that's been interpreted as igneous for convenience isn't igneous. Like the stuff here is. This stuff here is and stuff, and this is plutonic. But a lot of the quinnesec could just be, and that's what this is a passive margin type sediment seat. Like you have the quintussect volcanics, so your fault of your Niagara Fault would theoretically be in here. But there's no need for one. You have way over here, Dickinson County, you have the Felch Trough, and you have a little older sediments in a basin that was initiated early on in the Penokean orogeny. And we have detritus from that. This has to be. So while we were getting volcanics everywhere else, we were getting sediments here. But we have volcanics too. And the quintussect just easily goes into the bad water volcanics. Is everything the same age? No, these are individual flows and all that, and it hasn't been worked out. But we do have some dates. We have absolute dates. There's no need to complicate this by slapping a fault in here as a continental suture. And that's what this latest interpretation here does. Where is it? That's what this does. It kind of just shows you the Pembine Wausau kind of formed close to in place, not exactly, a few 100 kilometers away, a hotspot type scenario, and as the plate subducted, this one here, it caused extension, rollback, and we got the development of Pembine Wausau terrain in an Iceland type scenario. Except whether the hotspot was shallow or deep, I don't know. There's no way to know that. That stuff is gone. We can't tell. The rocks seem typically mafic. Doesn't seem anything special about them. So it probably was shallow. Now here's the map I did. Now here's a hypothesis that we might still have the Niagara Fault. But it's not this continental suture. This is where it's traditionally been mapped. And I have gone, where is it? I think I put it in here. Where is it? In Niagara, the town of Niagara itself. And there's a road up here. And you walk these outcrops, and they're deformed a little bit. There's some deformation like in the middle. Nothing really like hardcore. And the northernmost one shows no deformation. And then it's just no more outcrops. And that's conveniently where they draw this fault. Now, here's a cross-section, a general cross-section based off this. This is hypothetical. I am changing my interpretation a little bit based on field data. So I originally thought anticline, syncline this way, but now I think it's syncline, anticline. So we're going from north to south. The bottom here is south. I still need to work this out yet. I'm going to reserve that for a future publication. So it could be either or at this point. But like I said, that's what happens when you collect more data. And this is a biff in Wisconsin, a banded iron formation off the Roduct. It's a metabiff. It's highly metamorphosed. But it is banded iron. You can tell clearly that's the protolith. Let's see, are there any other photos here I want to show you? Here's a sub-area impact that happened at the same time as the Penokean orogeny. And that's kind of what this is. I originally thought that what I had pulled here might actually been the sub-area impact ejecta. And it's traditionally been marked as up here. But upon further investigation and further petrographic analysis, I now believe it is a kind of tough. It looks like a sandstone, but it's a tough. And there might be some sandstone with it. I mean, we had volcanism at the time, even during these banded iron formations, so it's not surprising. So it is older. At least I believe it is. Based on the field relationship. So this chart has changed a little bit, but not too much. The biggest change was that fault. Now, there's something else I wanted to say about the fault. I don't think I've done the map yet. Maybe I haven't, and I just closed that, didn't I? West Outcrop. Oh, these are my field notes. These are my field notes from April. You see, I scan them. So, yeah. Anyway, I don't need to show you too much of that. Back on track, Steve. So here, where is that thing? No, it's not. All right, so here we go. Zoom out. My God, man. I'm getting loopy off these shots. It wasn't the right thing. Let's see. Anything else here? I thought I had I'm starting to do... Okay. This is Niagara area, and here's these outcrops, and this is Niagara Sill. This is a volcanic unit. And you come here. This is not... I don't think this is volcanic. This looks like a gray wacky... It's got quartzite in it. Or it's an arcosic... It's a proto-quartzite. Something like that. And here you have metamorphic facies change here. And the line's not exact, but it's close enough. So you walk this here, and this has been traditionally mapped as Quinnipiac, but it looks sedimentary, or meta-sedimentary. That's what it's been mapped at, and these are the plutons associated with it. And then here we have the Niagara Fault, which conveniently hides itself from everywhere. And all of a sudden, oh, Michigami Formation, Slate and Graywacky, my bad, typo. See, you have this Niagara Fault zone, and then all of a sudden the lithology magically changes, but you start looking at these rocks, they're not that different. I mean, obviously the igneous rocks are different from the slate, but this stuff, there's Graywackys in the Michigami. There's proto-quartzites in the Michigami. So I don't see a need for this fault zone, at least not right here. So those are my references. So, yeah, there's this. The more I look at this Niagara Fault Zone, the more I believe it's a work of fiction. I think they thought they needed to put it in there to explain an accretionary terrain back in the 60s and up through the 90s and early aughts. But like I said, it works. It works without it. You don't need it. You know, if it formed close to in situ, you just get a back arc deposit volcanic setting, and this would be where your basically most of your Pembine-Wausau terrain was, and as that continental collision occurred, this would just crumple up. And as you can see, where's that other one? I do want to show you that. So it is possible that we might still have the fault, Niagara Fault. Like I said, I mapped it here, then I got sidetracked. And here's my cross section. See, I have it here. It might be here, but it's not a continental suture, and there's no need for one. Because we do know there are thrust faults within the Michigami and the area. We do know that. The Michigami did crumple pretty good. It deformed really well during this orogeny, as it was being deposited even. So, yeah, there's that. Anyway, I just wanted to give you... This is why I find it interesting, too, because it's just... And I'm not the only geologist that is shocked that you can't find the Niagara Fault Zone. No one finds it. There is, and let me show you some pictures. There is a good outcrop. Let's see if I can find it. Because these are the pictures, and they are logged. That's banded iron in Iron Mountain. That's by the dam. And see, this is mapped as Quinnipiac. Up past the hill that you can't see here, there is some volcanics, but this is clearly a slate. I mean, it doesn't get any more obvious. It's even got quartzite. Now, this is a gabbro. That's not at the dam. That's another place. But it's just like a fault of convenience to explain something that didn't need explaining. This is an interesting outcrop. This is supposedly 2,000 feet south of the Niagara Fault Zone in Kingsford, Michigan, right across the border from Wisconsin, just north of it. Now, you can't see really well here, but there's slate here. There's a lot of slate. You can see you've got folding, and it comes down and up, and you've got folds. You've got a lot of complex folding, and this stronger stuff appears to be Graywacky. I got to double check. It could be a tuff. That's why I got to go into the samples in the lab. But you can see this a lot of complex folding here, but there's none of this stuff's faulted. None of it. I would think being that close to such a big suture, you would have some faulting here, but you don't. It's folded. It's deformed, heavily deformed, but there's no fault. I've never seen even a minor fault in this area, you know, with more than maybe a meter of displacement. So why, and here you can see some, I think this is a different location. Yeah, this is a different place. Now here we do see some evidence of slickensides, not glacial striations, as some of these are. These are tectonically formed. And this is Westmore, Wisconsin. So we do see some, but the Niagara Fault Zone's nowhere near this, supposedly. And this is where we see some stuff that looks like high deformation with faulting. I don't know. It's a mess. Yeah, see, you can see the high deformation. These beds are highly foliated. That's a nice waterfall. I just want to show you some more. So these are all the pictures I take. Now, let me find that. This turned out to be the Randville. I was hoping it was Penokean. Then I went there and saw the pink. I'm like, it's Randville. This is that outcrop on the north side of this. It's the furthest north one here. So that photo you just saw is A. Right there. Where is the bloody thing? I don't want to close it. Okay. There's no deformation here. I mean, this stuff is just fracturing of rock. That's not a fault or deformation. It's modern. So there's no deformation here. You start moving south. You do see a little bit, and this is igneous. You do see a little bit of deformation. Where is? I think it's one of these 7A. I don't remember. I think it's here, right here. You see a little bit of deformation, which might be a minor shear, but we're still south of the supposed Niagara Fault, and this isn't a continental suture. I mean, this is what, 3 meters in width? It doesn't make sense that that would be a continental suture, but it might be a shear zone of some sort. Like it says, local, so that there. But you get further south, you keep going and going, and you get here. That is this F. Now this is what's mapped as Quinnipiac mafic volcanics. Now this outcrops behind a city depot, I think. This stuff, these are quartz veins. Now, still got to do some analysis. I got to do petrographic analysis to confirm this. But this looks like a protoquartzite to me. This does not look like it's igneous in origin. So, it's just, I'm not going to dog people that came before me. That's not the point of this. The point is we got more information now. We got better outcrops now. But there's still not a lot of outcrops. This whole area is still iffy. No one's ever drilled into it. There's water wells here, but it's all in the glacial stuff. No one's ever drilled into the Niagara Fault zone in this area. There's no indication of it in the subsurface or in any sort of aeromagnetic data or anything like that here. Now, may it exist further to the west and east? Maybe. But I'm just concerned with this area. It seems to be non-existent here or very minor, not as a continental suture. This cut my hand pretty good when I was out there. This is Niagara, Wisconsin, by the way, not Niagara Falls. So this stuff's clearly volcanic in origin. But then you got this part here, which looks more like slate. So here what we might have is a little bit of volcanics embedded with slate. So, which happens in the Michigami too. So I think these two are related. I think the Quinnipiac just kind of gave way to the Michigami. There's no need for continental suture and a sharp line between the two. It's just this stuff's definitely volcanic. That's gabbro, that kind of stuff. I'm just showing off my pictures now. It's my quarter for scale. This is, this is 12-foot falls, I think, and I'm pretty sure this stuff is slate. I'd have to look again. Yeah, it is, and this is right off the road, not that far. It's also a slate. It's just weathered differently, and you see this awesome quartz vein here. I measured all of these in here. See, these quartz veins are more common in the metasedimentary rocks than they are in the volcanic rocks. Does that mean they don't exist in the volcanic rocks? No, but they're very much more common in the metasedimentary rocks. The Michigami is loaded with stuff like this, and Pompelli's rules even expressed in some of them. But not so much in the Quinnipiac or the Badwater or the Hemlock. Probably because the Michigami wasn't indurated at that point, and you still had heat, even though you had solidified volcanics and sills, things like that. They were still relatively warm, and that would induce hydrothermal activity in the still unconsolidated overlying Michigami, which would pump these quartz veins through it. So that's probably why you see it in the Michigami more so than the volcanics. So a lot of this stuff that's been interpreted as volcanics seems to be metasedimentary, not meta-igneous. All right, anyway, that's it. I think I'm going to cut it off here. But anyway, that's it. If you have any questions or comments, please leave them below, and I hope you learned something.